Okay.
So, hello Abhijit, good afternoon. So,
Good
since you
afternoon,
are
ma'am.
the only one today, so let's have one-on-one conversation. So, how do you feel about the course?
Ma'am, till now it is going fine.
So, do you have any concerns?
No, ma'am.
So, today we'll, sorry,
Ma'am, someone has joined.
okay. So, today we'll solve problems based upon OTA. So, last time I asked a general question, right? What is the difference between an differential pair and an OTA? So now can you answer what is the difference between an OTA and a differential pair?
Ma'am, in OTA, the output is single-ended.
Mm-hmm.
In differential, it is differential output. Means between two nodes.
Two nodes, yeah,
We take output between two nodes.
right. And we have current mirroring action, like that current mirror bit. So basically, diode configuration is present in OTA, which is not present in the differential pair, right?
Yes.
So moving ahead. So this is the first question that we'll solve today. So in this question, see, this is an OTA, you can figure out, right? Since it is a single-ended output.
Yes.
So is working of OTA clear? How does an
Yes,
OTA
ma'am.
work? So basically what happens, so let's say in this particular configuration only, here we are giving positive delta voltage, so let's say plus delta voltage. So it will lead to increase in current by delta amount, right? So, or let's say small I. So for, when there is an increase in this particular transistor, since this transistor in series, so here also you'll see an increase of current by I amount. And since the current is increasing, the voltage at this node will change, right?
Yes, yes.
So if the current across this particular transistor is increasing, that means the drop across this transistor is reducing. Delta V across this transistor is reducing, right?
Yes.
Because the moment I increases, that means the resistance R will reduce. So it will result into reduction in V. So that means VDS of NMOS will reduce. So at this particular point, our voltage will reduce. So since the voltage is reducing at this particular point, so what will happen for this PMOS? This is connected to gate, so this node voltage will also reduce. And since this voltage has reduced for PMOS, we know VSG, right? It is VDD minus VG. And since this VG is reducing, so this VSG will increase. So resulting into increase in current at this particular MOSFET as well. This is clear, right?
Yes.
Now the same voltage, the same gate voltage is being applied across this PMOS. So there will be I amount of current flowing through this transistor, this PMOS also, the other side. And this we can know, we can call it as current mirror effect as well. So this is the similar action, how a current mirror circuit works, right? Just that it's in PMOS configuration. So now what about this transistor? Since this is in differential configuration, so what about this NMOS?
Ma'am, that voltage drop will be across parallel combination of above PMOS and NMOS, down NMOS.
So first,
That will
first
be,
things first, here, since this is in differential mode, so if we are applying delta amount of voltage at this particular input, first input, so here we'll have minus delta amount of voltage, right?
yes,
So if there is minus delta, that means the current has reduced.
yes,
So Here there is I amount of current that is flowing through this, but it is actually reduced, so it will be minus of I,
minus I.
right? So if
So yes,
but if I change its direction, if I change the direction to upward, then I can change the sign also, so this will be plus
yes,
I.
yes.
So
So
the
above I
current,
and I will combinely
yeah,
flow into output.
so combinedly we'll get output as 2I. So this
So
will be our I out. This is clear, no? So this is
yes,
how
yes.
a basic OTA works, right? Now coming to the question. So in this particular question, it is given that in this the circuit below, MOSFET follows this expression. Okay, so first of all, by looking at this current equation, what do we understand? What is it that is evident from this given expression?
MOSFET is in linear region, operating in linear region.
Linear region. Is it in linear region?
Ma'am, in saturation it is only K into VGS minus. No, it is 1 plus lambda VDS. That part is for yes, channel length modulation. Sorry,
Yeah. So
it is
what
in
is the mode
saturation.
of
Okay,
operation?
sorry,
MOSFET mode of
saturation.
operation? Saturation mode, right? Yeah. So this is clear. Next, what does this show?
Channel length modulation.
Channel length modulation. That is, GDS is not equal to 0. So we have
0.
to
Yes.
consider the GDS. Now moving ahead, K value has been given, lambda has been given. And so lambda for NMOS and PMOS both are equal. So lambda N is equal to lambda P is of
Point.
0.2 per volt millisiemen per volt. It's millisiemen per volt. And what is given? K is 4.34. No, it's this is per volt only. K is 4.34 millisiemen per volt. Yes, 4.34 millisiemen per volt, and lambda for N and P are equal. Now it says this I naught is 313 milliamps. So we have to find GM for NMOS. So how do we find GM? What is the formula for GM?
Delta ID by delta VGS.
GM is delta ID by delta VGS. So if we simply differentiate, so ID is, we know ID. So ID की जगह पे अगर we simply put D K VGS minus VT square 1 plus lambda VGS by D VGS. So what we will get? This is what we will get, right? And if we write it, or simply we can write it as 2 root K I naught by 2, where I naught by 2 is the current flowing through this particular branch. In this particular, okay, since we have this branch, so in this branch we'll have I naught by 2. So if no voltages are applied, that means for DC voltage, both branches will have I naught by 2 current, right? So this will simply become 2 times root over KID. That is what we are writing. You know? So now we have to substitute the values. So 2 root 4.34 millisiemen per volt into 313 So how much is the GM that we are getting? When we solve this expression, or like solve this.
Ma'am, 1648.28 micro Siemens.
Right. Correct. So this is what we are getting. Yeah. So moving on to the next question. In this particular question, what we have to find out, R naught is asked.
Or not?
So what is R naught? Since lambda is
1 by
given,
GDS.
yeah, R naught is 1 by GDS. And how do we relate GDS with
Delta ID
current?
by delta VDS.
GDS is delta ID by delta VDS. And since, so ID we know, it's by dVDS. So we'll get this is what we'll get, right? And if we see, this is basically the current equation in saturation, right? This is the
Yes.
current equation in saturation. K VGS minus VT whole square. So we can write ID into lambda, and here we know ID is I naught by 2. So our GDS will be lambda I naught by 2. So R naught will be 2 by lambda I naught, right? So we know the value of lambda, we know I naught, so we'll simply substitute and we'll get the R naught. So what is the value that we are getting? Lambda is 0.2. Lambda is 0.2 per volt, and ID is how much was it? Yeah, 313 milliamps. So this is what we are getting. The moment we substitute, we'll get R naught to be 31.948 kiloohms. This is what we'll get. Sorry, sir. Hello. Okay, so this is clear, right?
Yes.
Okay, so moving ahead with next question. So the next question is, what is the differential voltage gain for the given circuit above? So in this particular circuit, see, lambda n is lambda p. Sir, Raghavendra sir, can you turn off your mic? Yeah. Okay. So in this particular question, it is given that lambda n is equal to lambda p. Like this is a follow-up question from the first question, right? So lambda n is equal to lambda p. That means GDN is also equal to GDP, right? This is also known to
Yes.
us. So that means R naught n is equal to R naught P is equal to R naught. Okay, this is clear to us. Now it's asked differential gain AD. So AD we know it is equal to GM into Z out. This is known to us, है ना?
Yes.
Now so इसमें Z out कितना होगा? For this particular circuit, the above circuit, this is the circuit that we have, right?
Ma'am, can this be done by half circuit only?
Can this be done
It
by
can be
half
done,
circuit?
right?
Yes, we can do it. We can do it by half circuit method.
Yes.
So this is the output node. Yeah, this is the output node. The moment we are looking from here, what is the resultant impedance that we see? So the impedance due to this PMOS and the impedance due to this NMOS, right?
In parallel.
So these both will come in parallel. So if one provides an impedance of R0 and other is also providing an impedance of R0, so the resultant will be R0 parallel R0. कितना हो जाएगा? R0 by 2,
Or not by 2.
है ना? And GM. So GM कहाँ से आता है? From the transistor
Short
in which
circuit
we
test.
give input. और simply अगर बात करें, so the transistor to which we provide the input, it provides the GM in our gain.
Yes, yes.
ठीक है, क्योंकि ये जो GM है, this GM comes from input side.
Input MOSFET, yes.
Yeah, input MOSFET, input side, input MOS इससे आता है, and this comes from output node. Z out comes from output node. So यहाँ पे we'll take the GM for this particular transistor, which we have already calculated, right? GM ऊपर हमने calculate किया था, that same GM will apply over here. So how much was that GM? 1648.28, right? 1648.28 microsiemens. And we also calculated R naught above, है ना? So this is 31.948 kiloohms. So AD is simply GM into R naught by 2. That is 1648.28 microsiemens multiplied by 31.948 by 2 kiloohms. So how much is this? Final AD? What is the value we are getting for final AD?
Of 26,345, I think.
Yeah, 26.345 is the gain. And let's say if I want the gain in dB, then how much is it?
20 log of that.
So it will be 20 log of 26.345, which is
I mean, this question, is it asked in dB?
no, in this question it's not asked. I'm just discussing how much will it come. So first things first, is it log base what? Log base E?
Log base 10.
Log base 10? Sure,
10.
no?
Log base 10.
Yeah,
Yes, yes.
it is log base 10. So we need to keep in mind. This is very important. So how much is it in dB?
28.3 dB.
28.3 dBs. Because generally gain we report in dBs. That is the convention that mostly is used. So this gain is in volt by volt form. but mostly gain is reported in dBs. That is the common practice that is used. Okay, so moving ahead. So firstly, this is a new type of circuit given to you, right? So earlier in the circuit, we were providing both the inputs in differential mode, one with plus delta and one with minus delta. In this particular circuit, what is happening, in one terminal only we'll apply the input, and other terminal will get the input in feedback form. So here, what is the feedback circuit? So this path is feedback path. So generally, if you see a normal op-amp, let's say minus and plus, so we provide negative feedback for stability, right? Vn, let's say. Yeah. So this is how we provide the feedback, R1, R2. So here what happens? Yeah. So here Vout is getting connected to input node. This is Vn from virtual short. So Vout gets connected to Vn. So that is output gets fed back to input. Hence this is known as the feedback path. This one is the feedback path. So in this particular OTA circuit given in this question, this resistor based network, this resistor divider is basically behaving as a feedback path. Right? So here we'll only apply input to 1, and this point's voltage will change depending on the input applied. Okay, clear? So first let's read the question. So the circuit has been modified as below. The bias voltage is significantly large, that is VB, such that the devices conduct currents of I0 by 2. That means these both branches will have I0 by 2, I0 by 2. What type of current is this? The I0 by 2 current? Yes. What type of current is this I0 by 2 current?
What type of current means?
Means is this AC current, DC current, bias current? What type
No,
of current is this?
for DC current, for biasing.
Yes, so this is bias current. So this is bias current. So that is very important, we need to keep in mind. So this I0 by 2 never changes, it remains constant. Whatever we apply like small signal AC, it overlaps or superimposes with this particular current, but this I0 by 2 remains constant throughout your operation. Because first of all, we DC bias our circuit, then we go on by applying AC small signals for AC operation. This is clear, right, to everyone? So in this particular circuit, what we have to find is voltage gain. So first of all, let's solve this circuit, है ना? So for solving this circuit, yes. So in this circuit, okay, let's say if it was a normal circuit, so what should be the voltage at this particular point? What should be the voltage at that particular point? Here. Ideally, if it was a normal OTA, So my question is, what should be Vx? In this particular circuit that is shown below, what should be the Vx? Let's say Vn plus is Vcm plus delta, Vn minus is Vcm minus delta. What is Vcm?
Vx is VCM.
No. Acha, you are saying Vx is Vcm. Okay.
Common mode
Yeah,
voltage
why?
input.
Why?
Because in our input there will be average part plus differential part. Interference or interference.
No, my question is why VCM, like Vx should be VCM. You got it right. It will be VCM. But what is the
Why
reason
Vx
for?
is VCM?
Yes.
Because in that down branch, that is I naught branch, when we make small signal model, the current is 0.
Okay.
So that point should be VCM, because then only the left side current and right side current will be I or equal and opposite. We when Vx is VCM, then in left side the current will be VCM plus delta V minus VCM divided by resistance, and that same current will go from down to upside. That means in that down branch the current will be 0.
So you are saying in T1 the current will be K VGS minus VT, right? So VCM plus delta
Yes,
minus
VGS
VCM.
minus VCM.
So here VCM cancels, so whole square. So we'll have K delta square in T1, and in T2, let's say I2 will be K VCM minus delta minus minus VCM whole square. So this is K delta square again.
Yes, for these two currents to be equal, that Vx should be VCM.
And since these two are equal, but here we'll see a negative sign too. That is because this current is actually reducing in nature. In T2 it is reducing, and in T1 it is increasing. So this will be positive and this will be negative. That's why this negative comes into picture. Yeah, you are right. So basically this I1 that is coming, like increasing in this particular transistor, should not go to this tail transistor. This is not allowed. So what should happen? This I1 should transit to this branch, so that this excess current should be managed in the above part only. It should not affect the tail current source. This is clear to us, right? So keeping this in mind, can you tell me what should be the value of Vy in our actual circuit? In this basic circuit, Vx was Vcm. So what should be the Vy in this above circuit? Anything that comes to your mind? Okay, so let's look into it. So basically we got Vx as Vcm, and if we want to write it in terms of Vn plus and Vn minus, how can we write? So Vn plus was Vcm plus delta, Vn minus was Vcm minus delta, and we are getting Vx as Vcm. Is there a possibility to write Vx in terms of Vcn plus and Vn plus and Vn minus?
Vn plus Vn minus by 2.
Yes. So Vx was basically Vn plus Vn minus by 2. So we are getting Vcm plus delta plus Vcm minus delta by 2 as Vcm. So in this particular circuit, now in this particular circuit, what should be my Vy? It should be Vn plus plus Vn minus by 2, similar to the earlier case. Vn plus is how much? Vn plus Vno. It is actually Vn. Vn
Yes.
minus is how much? So it's actually connected in feedback path. So if I want to say this node and this is actually my Vn minus, how much will it be?
And it will come by superposition of V out and VB. Right? That by
Yes.
voltage division.
By voltage division, right. We'll get it by voltage division. Okay. Yeah, so we'll get it by voltage division. So bias voltage VB is sufficiently large, it's given in the question. And V out is present. So this is VB. So if it was, let's say, when we are performing AC analysis, see, first things first, the gain that we are finding right now is AC gain, right? So always whenever we are finding the gains, we are finding small signal, we are doing small signal analysis and we are finding the gain. That means we are finding AC gain. So AC gain mein what is the first things that we should do? We should put DC points to ground, right? This is what we
Yes.
do, DC points to ground. What is VB? VB is a DC bias
VBS
voltage.
DC.
DC bias voltage. So that means this VB will be AC grounded. This is AC ground.
So
So
V minus will only due to V out.
yes, VN minus will be only there due to V out. So now what will be our VN minus?
R1 upon R1 plus R2 times
Yes,
V out.
yes. So this is what is our V in plus and V in minus. So we'll get our Vy to be, so let's say R1 by R1 plus R2, we name it as K for our simplicity, okay? It's a constant, simple constant K. So we'll talk in terms of K, then we'll again resubstitute. So this will be plus KV out by 2. So this is what we got it as Vy. Now we have got our Vy, okay? So see, the small signal current, I'm writing it by small I, okay? Small I. So the small I in this transistor, and we'll make another assumption before starting only, that is GM is much higher than GDS. So we are neglecting GDS, okay, to make our lives easier, to make the calculations easier. That is the only reason we are going ahead. And in general also, you can observe that GM is actually in millisiemens, whereas GDS is in mostly in microsiemens. This is mostly the case. So there is a 3 orders of difference, so we can safely assume this, right? So this is the assumption, okay? So moving ahead, so in general, MOSFET current equation in small signal, how can we write universal MOSFET's equation for small signal model? Universal current equation for MOSFET for small signal model. How do we write?
GM VGS
Hmm.
plus GMB VDS.
Yes, GMVGS plus GD GDS, right? This is the GDS that we were talking. So here we are considering GDS to be 0. So उससे क्या होगा? We need not to consider the effect of VDS. So this is the best part. Now moving ahead. So this is my transistor 1, transistor 2, transistor 3, transistor 4. So ID1 will be GM VGS. VGS कितना है? VN minus this is gate, drain, source terminal. This is gate, source, drain terminal, source and drain terminal, drain, source and gate terminal. Okay. So it will be VN by 2 minus KV out by 2. So ID1 is GMVN by 2 minus KV out by 2. Right? This is ID1. We know since these two are in series, so T3 and T1 will have same current. So that means ID1 will be equal to ID3. This is clear to us. And since we are not considering the effect of VDS, so our current is only the function of VGS. And if we observe carefully, the gate terminal of both T3 and T4 are shorted. That means they both have same potential. And source is also shorted. And it is also AC grounded, right? So source is also shorted. So our current through the transistor 4, that is ID4, will also be equal to ID1 and ID3. This we can also name it as mirror effect. This is how mirror circuits work, right? Current mirror circuit. So this is clear now?
Yes.
Yeah, this is clear, right? So now ID1 is equal to ID2 is equal to ID3 and ID4. ठीक है, तो यहाँ तक we got one current. Now what about the current through transistor 2. So let's write the current through transistor 2. क्या होगा? ID2 will be GM. Again VGS होगा GM VGS. So that is KV out minus VN by 2 minus KV out by 2. Right? So ये कितना हो जाएगा? GM KV out by 2 minus VN by 2. So if you observe it carefully, so ये करंट का डायरेक्शन कैसे होगा? ID2 का डायरेक्शन इन ट्रांजिस्टर 2 अपवर्ड्स होगा. नहीं ये इक्वेशन
मैम दिस
जो
इज
देखो, जब when we are saying ID equal to GM VGS plus GD VDS, the current flows from drain to source always for an NMOS. ये समझ में आ रहा है मैं क्यों बोल रही हूँ?
यस
क्योंकि when you see a small signal model for an NMOS, so this is how your model looks, right? Draw it clearly. What is the direction of current? तुम जो इक्वेशन लिखते हो आईडी का इक्वेशन कैसे लिखते हो? You simply write it from here, right? GM VGS plus 1 by R
यस
naught VDS. This is how we
VDS.
write the equation. This is how we get the equation. इसमें if you clearly observe, the flow of current is from drain to source,
ड्रेन टू सोर्स
है ना? तो यहाँ पे भी this current is actually from drain to
ड्रेन टू
source.
सोर्स
But if you observe it carefully, it is ID2 is minus of
माइनस ID1
ID1. This is clearly evident, है ना? So if ID2 what I have written right now is from drain to source. अभी yeah. Yeah, so this is how we have mentioned our ID2. Oh, sorry, small ID, no? Small ID2. And this is ID4, 3, 4, 1 and 2. So if I want to write ID2 dash, let's say, to be minus of ID2, and what I'll do, I'll simply change the direction. This I can do it, right? Because I'm inserting a minus, that means I can change the direction, है ना? This I can safely do. तो ID2 dash कितना हो जाएगा? It will be GM VN by 2 minus K V out by 2. This is ID2 dash. So if you observe carefully, the current from this output node, I'm writing it as I out, it is actually equal to ID4 plus ID2 dash, right?
Yes.
So we'll simply add these two. So it is 2 times of GM VN by 2 minus KV out by 2. है ना? So this is your I out. This is expression 1. Now I out 2 can be written as something, some other way also. It can be expressed in some other way also. How can we express I out? One way is this one. We got it already. What is the another way in which we can express the I out? Yes. Looking at the circuit, let's say this is the current I out coming. So how can we express I out? Can we write it as V out by R1 plus R2? Can we write
Yes.
I out as V out by R1 plus R2?
Yes.
This is clear, no? So this is expression 2. We'll simply equate these two. So how much was K? It was R1 by R1 plus R2, right? Plus 1 times, oh, etc. We'll have K3. So GM, yeah, into V out is GM times Vn. This is the expression. We clearly know that GM R1 is much greater than 1. This is understood, right? Okay, R1 is in few kilo ohms and GM is in few milliohms, so then too it will be greater than 1. Much nahi to at least greater than 1. So we can simply write GM R1 plus 1 to be GM R1. So say what will happen? GMVN will be GMR1 by R1 plus R2, GM cancelled. So we have V out by Vn to be 1 plus R2 by R1. So what is this that we got? What is this expression?
Voltage gain, no?
What type of voltage gain? Yes, this is voltage gain. What type of voltage gain? Is it common mode or differential mode?
Differential mode.
Yes, it is differential mode. It is differential mode. So we got the expression for differential mode gain. We have solved this expression, solved this circuit, and we have finally got the expression for differential gain. What was the question that was asked was to find the value of voltage gain. What is the voltage gain? We have found the expression. Now what will be the value? AD kitna aayega? We'll simply substitute, right? 1 plus 8 by 5. How much is this?
2.6.
Oh wait, R1 is 8 and R2 is 5. Oh, okay. So here actually values R1 is 8, this is 8 and this is 5. Yes. So ये उल्टा होगा. So it will be 5 and this is 8. So it is 13 by 8. Yes. So how much is the AD that we are getting?
1.625.
1.625. And how much is it in dB? Because practically gain is reported in dBs. So
4.2 dB.
4.2 dB. So this is the final answer. Got it? Understood?
Yes. Yes.
So is this derivation clear? We went on
Yes,
a
ma'am.
step by step, right? थोड़ा lengthy derivation है, but it's very simple derivation. है ना?
Lengthy but very well explained by you.
You got it, right?
Yes,
Everyone.
ma'am.
So you understood, no? So we started with very simple circuit, this circuit. It was explained just to make you understand the importance of this Vx point. That is this tail transistor's drain voltage, how much it should be, right? So we analyzed this circuit to understand that particular point, and by using that particular concept, we applied that concept into this new circuit that was given to us in this particular question. And we found that this Vy, that is the drain voltage for the tail source, we found out Vy to be Vin plus kV out by 2. Now once we got this V out, so this is basically source terminal for both the NMOSes. And that's why this point is important, because our current equation, universal current equation, is Gm VGS. So we need the voltage at S. So that's why first we found out this Vy, which will act as the source voltage for both the NMOSes. Then we moved ahead. We said that in universal current equation we'll neglect the effect of GDS. And this assumption is safe to make because GM is much greater. That is, there is at least 3 orders of difference between GM and GDS. So that's why we moved ahead with this particular assumption. Now we simply applied the universal current equation. We solved it for input circuit, this input half circuit first. Then we applied the current mirroring so that we find the current for this transistor T4. And again for transistor T2, we applied the same universal current equation. Right? So that's what we did. After that, we simply here this part, here nothing has been done. Simply what we did, we got an ID2. This is for for transistor T2. But we know that the current coming out of an OTA, like basic OTA, is 2 times I, right? So that means one component of current comes from the top PMOS and other component comes from the bottom NMOS. Here, from the expression that we got, the current's direction was opposite. So it was from output node to the tail transistor. But we wanted opposite, so I simply added a negative to just change the sign of it. Now once we change the sign of it, it comes in simple form where the current from the PMOS and NMOS merge at the output node. That's how finally we get our circuit. So here we simply applied that particular expression and we solved. So we got our I out to be this. Now if we clearly observe in this particular circuit, this output current will flow through these resistors pair, and the drop across these two resistors will give us output, voltage output. So we can simply write our output current as V out by R1 plus R2. Then we simply equated these two. We simply equated these two equations and we have solved it. Finally, we got our gain to be 1 plus R2 by R1. Clear, no?
Here, ma'am.
Yeah, hope this is clear. It's a bit lengthy, but very simple. You can simply sit back and look into it once with a very calm mind, you'll understand everything. Now, Yeah, so this is another type of question that I found. This is also something very interesting. Okay, since we have very less time, so I'll quickly go through. So in this particular question, see, fundamental like constants have been given, like parameters, GM has been given, R naught has been given for both your NMOS and PMOSes. And this extra resistor R has been given as 1.8 kilo ohms. You have to find differential gain. So when it is set differential gain AD, we simply know it's GM into Z naught, Z out, right? This is what is known to us clearly. Now, see, here also, if I go for half circuit analysis, and this point we simply connect it to ground, right? Because we say that this point is not affected because of our small signal. So now considering this circuit, so to make this circuit symmetric, what I can do, as we did it last time, we can simply divide it into two resistors, each of R by 2. This was of R, so each resistor is of R by 2. So your half circuit, how it will look like, this will be a PMOS, this will be R by 2, and this is an NMOS, VA, and here it will be ground, and here also it is grounded. This is VDD, and if we see carefully, here this is also a diode connection. This connection is also a diode connection, but they have been cross coupled. So here, rather than connecting the gate of same PMOS with its drain, what has been done, the gate of first PMOS like T1 has been connected to drain of T2, and gate of T2 has been connected to drain of T1. Okay, and when we are biasing, at that time both the sides will have same amount of current, and since both the transistors are matched, so it is safe to, or it is equivalent to the diode configuration of transistor in itself. Is this clear? Like gate of the transistor getting connected to its drain is equivalent to this cross connection. If since both the transistors are matched and same amount of current is flowing, so during biasing at least this is safe to say that this is simple diode connection, right? So half circuit हमारा कैसे दिखेगा? It will look somewhat like this. Now, oh no, yeah. So this is how our circuit will look like. So now what we have to do, this is our V out. We have to simply see, this is the input, so input GM will come from this GMN, which has already been given. The only thing we need to find out is Z out. So how much is the value of Z out? So from looking from this
Three
particular
resistors
code,
will be in.
we'll get, sorry,
And three registers will be in parallel, looking
yeah,
up,
yeah,
looking down, and R
looking
by
up,
2.
looking down, and R by 2. So looking up, we'll have R naught P parallel with R naught N, which is downward, parallel with R by 2, and parallel with, actually this is a diode connection, no? So because of this diode connection, our Z actually turns out to be, for diode, Z diode,
1 by GM,
1 by GMP
GM plus
plus
GDS.
GDP, right? So that factor will also come into picture, so it will be 1 by GMP. Clear?
Yes.
So this will also come into picture. So यहाँ पे we'll have all these in parallel. This will give us the Z out, and simply we'll substitute the Z out over here, and we'll multiply it with GMN, and we'll finally find the AD. And the value for this AD is 3.0 3.535. Yes, this is minus 3.535, and here it is minus q, because what type of configuration this is, we also discussed it last time. It is
common source.
yes, this is CS configuration. So since it is a CS configuration, we'll definitely get the gain as negative. So we have to simply apply that. Clear?
Ma'am, you did that cross connection. You replaced it by diode connected,
Diode connected.
like diode connected.
Yeah.
So can we say like this that both transistors are matched?
Yeah.
So
See,
the
how we
drains
know how?
drains are
Yeah. So what I'm
drain
saying
of both
is,
are like equal drain voltages.
no, see,
So that drain can be connected to this side.
yeah, I understand your feeling, but first of all, before applying any AC signal, we have DC biasing for the circuit, right? During DC biasing, we know that this half circuit will have I naught by 2, and this other half circuit will also have I naught by 2 current flowing through it, right?
Yes.
These two currents are equal, and since both the NMOSes have same parameters and both the PMOSes have also the same parameters, that means both the PMOSes are matched and both the NMOSes are matched,
Yes.
right? So that means whatever voltage you'll see, now since I naught by 2 current is flowing in both the branches, so here you will see some drop across this particular node, and if you analyze, that same particular drop will be here as well. So both the
Yes.
nodes will be at same voltage.
Similar drops and
Yeah,
similar voltages
similar
on both
voltages.
sides.
Yes. So see, because you cannot keep this connection, this diode connection, to be floating, right, when you are going for half circuit analysis.
Yes.
So what is the better way to put it down? So we can make it normal diode connection, because it is safe to say, right? Because now when you are seeing an ideal biasing condition, you can clearly see that both these terminals are at same potential. Everything is same, and all the transistors are matched, and they are like replicating one another. The one half circuit is replicating the other. So it is safe to say that these two, other than this cross connection, they are simply diode connected, right?
Yes.
Yeah. So it makes the analysis much easier. That is the only thing. Clear?
Clear.
So yeah, it's already an hour. So today we don't have much strength. Like we only started with single student. Now also we have just 2 or 3 members. What's going on? Is
Still, you continued.
No,
Thank
see,
you for
I
that.
have to continue. Even if there is no
Yeah.
person, also I'll continue. And thank you, Abhijit, for being present. It was wonderful. At least you were there. But see, if nobody is there, also then also I'll continue. That is not the point. But the thing is this helpful?
Yes, ma'am. Very helpful.
Are live sessions
Very
making
helpful.
you solve the problems? Are your doubts getting clear? Is it helping
Yes,
in
ma'am.
any way?
Yes, ma'am. For solving assignments, they help, and also for understanding
They
and
help,
for
right?
yes,
Okay.
by interaction, our doubts are clear.
Yeah, so that is the only thing, because today we started off only with you, right? You were the only student
Yes,
who
yes.
was present, so that is the thing. But yeah, then
And at
too.
starting, I felt that you will not continue
No,
because very
I'll definitely
one or two
continue.
people.
I'll definitely continue. See, if nobody is present also, then also I'll continue, and lecture will be uploaded on YouTube. But it's just that if few people are present, so you people see, I'll teach according to my personal experience and my knowledge, where all we can have or we can face doubts, I can pinpoint that thing. But when you are present in live sessions, so you can come up with some point or some doubt that I might miss, or I can feel that this is understood to everyone, but that is not the case always, right? We all
Yes.
understand at different points and different levels. So that is the only concern. Otherwise, but thank you, Abhijit. Thank you for being present. And
Yes, ma'am. Thank you.
yeah, so hope to see much more students in coming weeks. But thank you so much. Have a wonderful week, evening
Yes,
and
ma'am.
week
Thank you.
ahead. Yeah, thank you.
Yes.
Bye.
Thank you.
Thank you, ma'am.